Perfect. All right, looks like we already got a good number of people. So I think we'll start slowly, but get started just so we have still a lot of content today that we want to fit in. So today, I want to talk to you about tuning Postgres Autovacuum to improve performance and reduce bloat. Now, this is a complex topic and there's a lot of slides, but I hope to fit this into roughly 45 minutes, and then we'll have time for Q&A at the end. You can also put questions in the Q&A box in Zoom throughout the webinar, and we'll get to them mostly at the end. But if there's something that pops out, we may take it during the webinar as well. Now, you may also see Manuel from our team in the chat. As we go through the webinar today, Manuel is going to paste useful links that relate to the topic at hand into the chat, so you have some more background information when you're interested in that. Now, I also want to give a shout out to the rest of the pganalyze team, and specifically Maciek and Jens in our team, because a lot of this webinar today is really based on research we've been doing for the pganalyze product and for upcoming advisors that we're building into the pganalyze product. And today we're really going to talk about the underlying tuning concepts. So you don't need to be using pganalyze to make use of this, but it does go well together. And we'll also share a recording of the webinar by email, most likely tomorrow, including the slides. So if you have, something on a slide that you didn't catch in detail, you can look at that later and also share it with colleagues. Now we'll talk, as mentioned, about a lot of things today. So we'll start talking about a little bit of the physicality of tables, like how are tables actually laid out, because I think it's a very important context for everything else. We'll talk about transaction IDs and all the trouble that they call this. We'll talk about what all visible pages are and how to impact query performance. Then we'll switch gears a little bit and talk about Autovacuum scheduling and things like cost delay and how to tune cost delay, as well as aggressive and the new Failsafe vacuums. And then we'll close by talking about a few edge cases like that Tuples not yet removable that can cause vacuum to not do any work essentially. We'll also talk about a few special cases in the cloud. I'm sure a lot of you here today are using Amazon RDS or Google Cloud SQL. And so in those cases, including Amazon Aurora, of course, Autovacuum is important, and Autovacuum also needs to do its work. And there are a few special tunings you have to be aware of when using these providers. And at the very end, we'll talk about estimating and fixing table bloat. Really, a lot of this is related to bloat, but when you already have bloat, then there are a few specific steps that you want to take to fix that we'll talk about at the end. Now, I want to start with, kind of pondering a little bit how tables are structured and just sharing with you my understanding of why this whole, bloat situation is a problem. Now, I like to think of Postgres tables as many things because they're complicated, but most recently I thought of it a little bit like a housing block of an American city, right? So they're like laid out in the grid and they're there, right? So people move in, people move out, but the city streets keep staying in the same way. And you can think of, Postgres tables in the same way, like rows come and go, but the tables are still there, right? And so a lot of what we'll talk about today, again, comes down to there is a file that stores your table, and that file has certain size and has certain structure, and that's really causing a lot of the Autovacuum kind of situations. Now, this is a table. It's a small table. So this is a table of about 100 kilobytes. Each of these little green squares is 32 bytes. And each of the larger kind of surrounding black squares is 8 kilobytes. Now, the reason I chose 32 bytes here is because that's the level of resolution that Postgres tracks its free space map at. So in a sense, this is to Postgres beautiful because for now we say green is free here. So this means there is a lot of space for data. Now, when we create a table, technically we don't yet get a lot of details, but essentially imagine we have one page, right? And that one page has one metadata information in the beginning, right? So the very first block of that page, or the very first part of that page, is essentially storing how many rows are in this page. And when we say page, again, we mean this 8 kilobyte block of data. Now, when we insert data into this new table, into this test table here with 2 columns, then we essentially start inserting data into these pages, right? So here you can see the data kind of gets added at the end. And so we created this, test table. We added the value short that takes up roughly 64 bytes. So it takes up 2 of these squares. Now, if we insert a very long value, then it's going to take up more. So it's going to take up 5 squares. And there's a kind of a subtle point I want to make here, which is if you have large values, right, that does impact how things like vacuum work, how bloat works, how when you look at the density of pages, all that stuff really depends on the shape of your data and how many columns you have and how long your values are. Now, we keep doing this, right? And we keep doing this 48 times. And what we then get is 50 live tuples. And you can see here, so blue again are kind of the actual live rows. And so you can see that this one page of 8 kilobytes is pretty packed by now. Now, this is an actual table that I created to test with. And so I'm using the pgstat tuple extension, which is part of the contrib module in Postgres, to look at how, what statistics do we have available about this. And you can see here, there's a couple of details about the tuples in this table, right? So we have 50 of them, the length, so kind of the summarized size of them, and how much % of the whole table they make up. We also see dead tuples, which we'll get to in a moment, and we see the free space, which is pretty much non-existent right now. And one thing you can capture here is the kind of live tuples per page density, which means on average, how many live tuples are there, like live row versions are there on each page. And right now that's 50, right? So it's pretty good in the sense that we have a lot of data compressed in small space. Now we insert one more value, and what happens is Postgres has to extend the table. So Postgres allocates a second page, and now our tuple density, of course, drops, right? Because suddenly we have 2 pages, one of them pretty empty, right? So this is hopefully pretty standard, not too surprising to you. Now, what happens when we do a delete, right? And for posterity's sake, we'll delete everything except the very last thing we inserted. Now, when we insert this, when we call this delete, we are essentially causing all these 50 rows to become dead row versions, dead tuples. And what that means is that our page density, as we measure it as live tuples, went down quite significantly, right? Because we still have these 2 pages, but now all this data is kind of dead and unusable. And you can see that also in the pgstat tuple data on the left here. Now, there's an interesting and important aspect to understand here, which is the concept of time, right? So we have this physical table that exists and time is passing and we're doing activity on a database, like we're doing updates, we're doing deletes, we're doing inserts, we're doing all these things. And if we have no vacuum, what happens is we insert 50 more rows of the same size, then Postgres will extend the table again, right? And Postgres will keep doing that as it needs to do, but these dead rows are going to block kind of, us from reusing that space. And really, this is the whole point of vacuum, right? Is that we don't keep growing the table for new data, but we can actually reuse the space that we have here. Now, we vacuum the table, right? Now all this kind of unusable space becomes usable. We now have one live tuple. Our live tuples per page density, though, is still quite low, right? So between us vacuuming and not vacuuming, it didn't actually change how much, pages we have. And that's because vacuum will not remove pages, except if they're at the end of the table. But in this case, right, like we have the empty page at the beginning of the table. And so vacuum is not going to remove that. And really, this is bloat, right? There's a lot of definitions for bloat, but this is my definition of bloat, is when you see something like this, right? And if you look at pgstat tuple and you vacuumed recently and vacuum was doing its job, and you see a high free percentage of the table, like a very high free percentage, right? 98%. And you have a low tuples per page density, this is, what to take care of. And it was a question when we'll send out the recording. We'll send out the recording tomorrow by email, just to go. Now, really Vacuum's first job is keeping excessive bloat away, right? So the point is we want to turn that tuples into free space before we need that free space, which means Vacuum needs to run frequently enough to make space reusable. Now, when Vacuum didn't do this first job, then you probably need pgrepack to fix. We'll talk more about that later, but this is something I ran this weekend with some preparation by a colleague of mine. And this was a pretty drastic change on a table where we had a lot of this bloat, right? And the table went from 500 gigabytes or 460, 70 gigabytes to 9 gigabytes, right? So an order of magnitude, big an order of magnitude improvement in the size, just because the table was so bloated, right? That 3% was so high. I'll talk more about that later. Now it's time for the transaction ID clock. Now, this is a very important thing to understand with Postgres. In Postgres, it is necessary to vacuum every table in every database at least once every 2 billion transactions. I believe there's a quote from the Postgres documentation. So this means once you have run 2 billion transactions on your database, right? So you've done your writes, your updates, your deletes in a transaction, and you've assigned 2 billion transaction IDs, then you must have vacuumed every database and every table during those 2 billion transactions. Now, short detour to the Postgres source, at least an excerpt of the Postgres source. So transaction IDs are the simple normal transaction IDs are 32-bit, and they're 32-bit unsigned integer. What that means is that the reason we have to worry about this is really just the fact that there is literally a variable that we have that is 32-bit sized, and it runs out of space. Now, you might ask, why not just increase the size of the variable? Believe me, there's a lot of conversations on a Postgres mailing list to improve the situation. It's complicated. We won't talk about that today, but just believe me, it's not just a question of changing 32 to 64. Now, what happens when we reach the end of this unsigned 32-bit integer, right? So we get to 4 billion unique values, then we wrap around and we essentially, get to 0 again, just by the way machines work. And so Postgres has a little trick here, which is important to understand, which is Postgres actually reserves the first 3 values, so 0, 1, and 2, for special kind of purposes. And so they're really the one normal transaction ID 3, and there's a very important one, which is the number 2, most people will talk about in a second. Now, these transaction IDs are stored in what's called the tuple header. So again, tuples are row versions, right? So what's stored in your data, in your tables. And each of these rows, each of these row versions has a header, and the header has an xmin or txmin and a txmax. Now, the most important thing to understand is a txmin gets set when you're inserting the data, right? Or you're creating the tuple. So that means at that time, you're essentially just saying, what's the current transaction ID for the transaction I'm in? I'm writing that to the table, right? And so I'm writing this 32-bit value to the table. Xmax is used in deletions and in some locking cases. Now, this xmin determines which connection, and this xmax determines which connections can see this row. So imagine you had a connection that has an xmin, horizon is called, which is the connections view of the world right now, consistent as of this transaction ID, right? Which is 5, right? So the backend kind of has an xmin 5. And on the right here, we have 4 tuples. We have one with xmin 3, one with xmin 4, one with xmin 5, and one with xmin 6. And let's suppose that the third one was actually one to be inserted, right? And so what we can see is that we can see the first 3, but we cannot see the 4th, because to us, to our connection, this tuple, this row is in the future. And this is a very important concept because the way that Postgres handles concurrent behaviors, right, concurrent inserts, concurrent selects, or selects concurrent inserts, is for this xmin and MVCC handling in Postgres. And so this is a fundamental function of how Postgres works. It's not something you could just turn off, but a lot of the complexities come because of these visibility rules that we're handling here. And you can actually query for this, right? So if you're interested in understanding what is my own, like me as a connection, what is my own xmin, I can actually just go in and query that xmin from the peach selectivity table and get my own xmin back. All right, now let's talk about this very complicated diagram here. It will hopefully become clearer in a second. So think of 32 bits, as a finite space, right? And so you can kind of think of it like a clock, right? A clock has 24 hours or 12 hours, depending on where you live. But let's say it's 24 hours, right? So that means in a sense, it has, if you just look at the hours, it has 24 unique values, and then it wraps around and becomes 0 again or 1 again. Now, the same thing happens with transaction IDs, right? So you're going around the clock, in this example here, clockwise. And so as you're increasing them, right, you're kind of moving your dial, and then you kind of come around and you get to the same value again. And the way that Postgres treats this 32-bit space is it actually splits it in half. And right, so 4 billion is what the number of values we have. 2 billion of these values are transaction IDs that are in the future. And this is as of a backend doing work right now. 2 billion transaction IDs are in the past, which are transaction IDs that have been assigned to someone and that have been written to disk most likely. And what this lets us do is do some very simple math to understand, are we supposed to see this, row, this tuple, or are we not supposed to see it just based on where, it is at in relation to our own ID? Now, there are 2 important values to understand. There is the oldest transaction ID that's in the past, and the newest possible transaction ID in the future. right? So as we move the dial, this changes, like we kind of, keep incrementing, which is the oldest transaction ID in the past, and we also keep incrementing the newest possible transaction ID in the future. Now, the really bad thing that can happen here, and it doesn't actually happen because Postgres stops you from doing this, is imagine that the dial moves, but we still have this old transaction ID that's supposed to be in the past. And technically what would happen is you move the dial, right? Time passes, you're inserting new transactions, and so you're causing data corruption because a row suddenly disappears because it's in the future, right? So clearly this would be a bad idea. But the reason we care about this and the reason we do all this transaction ID wraparound business is because we want to prevent this data corruption that would happen otherwise. Now, Postgres does something called freezing. And freezing is a bit of a complicated concept. It's also kind of simple, but it's something that takes a little while to kind of really get to you and really have an intuitive understanding. And I'm not sure if I fully comprehend every detail, but I feel much better now after a couple of weeks of studying this. And so freezing is when you have a transaction ID here, and instead of actually storing the transaction ID, like treating the transaction ID as an actual number, it gets frozen. And so frozen XID or frozen transaction ID is a number that's infinitely in the past, essentially. So it's not, there's no chance that if, we compare it with any transaction ID value, it's always going to be older than that. And what that does is it moves this transaction ID out of the process here, right? And so imagine again, a physical row version, right? Like that's on your page. That one has a frozen transaction ID that's marked. That means that transaction IDs can keep advancing, can keep wrapping around, and the frozen XID doesn't have to care. And this is really important because that way old data, right? Data that we just want to have existing in our tables can remain there and does not need to be modified anymore because it is frozen. Now we keep, kind of doing this. Now we have frozen it, right? So now we can succeed. Everything looks great. Now, what happens in practice is we actually freeze a lot earlier than we need to, because you don't want to do this right when, you need that new transaction ID, because really you want to do this ahead of time. And this is where Vacuum comes in. Now Vacuum's second job, right, is preventing Postgres from running out of transaction IDs it can safely assign. So this is the fundamental job of Vacuum, and has to do that by freezing old row versions ahead of time. Now, the third thing that we need to talk about in terms of why Vacuum exists is all visible pages and slow queries. So kind of simple example to start. So imagine you're reading from this table, right? This table that we looked at earlier. And we're just looking at half of it just to compress the space a little bit. So when we're reading here and we're counting, from this table, in the most simplified example, we have 2 rows here. That's 6 pages. So we need to look at the 6 pages to find out if there's data. And then, we return these 2 rows with 160 bytes each. So in a sense, we're reading a lot more data than we need, right? We're reading, I think 50 kilobytes roughly, but we only need 160 bytes. That's kind of pointless. Now, imagine that there's an index, right? So one benefit the index has is the index tells us where exactly in the table to find our data. So imagine here we have an index on data and we're searching for the value short. And then we, have 3 entries that match that value short. And so the index tells us where in the page to find that data. Now, there's an interesting aspect here, which is, in the first place, we started select ID. Now, the index does not contain the ID, so we have to go to the table. But what if we just care about the count or some other column that's in the index already? Now, do we actually need to go and access the table, right, in this situation? And this is complicated. I'll summarize it for you. There's a visibility map. And the visibility map is used for index-only scans, amongst other things, to determine whether Postgres needs to go and check what's in there, right? Like if the visibility map says something is visible, then Postgres does not need to go to the table. And so the way to think about this is you're vacuuming your table. Now Vacuum knows that the data that's in this table is visible to all current connections, right? So there's no connection alive or nothing, no other object alive that is in the past before, the data in this page. And so when you vacuum it and that is the case, then the whole page is marked as all visible. If there's any modification, then that page loses the all visible bit, right? So if you do any update that affects this page, it will just blow away the all visible bit, and Vacuum will come around again and fix it and do its job. But the all visible bit has two purposes. So first of all, it helps us when we do the next vacuum and there was no modification to the page, we can actually skip that page during vacuum, which is super helpful, right? Because vacuum otherwise has to look at everything. Second thing is it allows us to do index-only scans. Now, when we do index-only scans, in this particular case, we have a visibility map, and the visibility map is, again, a very tiny portion of data. And what it does is it says, oh, you know, you don't even need to go to the table to check if these rows are actually visible, if these rows are actually existing for you, because they are infinitely, you know, in the past, from this context, right, that they're visible. And so it's cool, you just don't need to check. And so this turns a, you know, what could have been 3 table pages to look at into 12-bit of data to look at, right? Much, much less data. And when you look at an explain plan, you can actually see this by, again, looking at index-only scan. If you look at the heap fetches data point here, so the top one, I was querying the next best table I could find. I just, you know, ran a select count star where a certain ID is a certain value. The index helped me answer this. But then because of this visibility check, Postgres had to go to the table to check. And so I had one heap fetch for one result. Now I did a vacuum, and then you can see that the heap fetches are now 0, and our shared hit also went down by 1. So we had 1 page less to visit. Of course, if you have a big table and a lot of results, these numbers will be much higher, right? So here it didn't matter much from a performance perspective, but it could be much more significant. Let me just do a quick pause, see here. We will talk a little bit more about deleted tuples, I think, and then we won't talk much about covering indexes, just so you know. Now I want to summarize again the 3 main goals of vacuum. So first of all, the main goal is reducing table bloat, right? That's the main benefit to your application. The second goal is preventing transaction ID and MultiXact wraparound, as we just talked about. MultiXact we'll talk about in a moment. Now, third is we mark the pages all visible to prevent repeated work and enable our index-only scans. And really, this is the whole reason we do vacuum, but they're all important, right? Like we don't want table bloat, we don't want to have a crash on our server, and we kind of want to have fast queries. Now, let me take a sip of coffee here. All right, so let's dive into Autovacuum. So Autovacuum, you know, does a lot of this work for us. And Autovacuum, the way you can think about it is there's a fixed number of or maximum of workers. And this maximum of workers is defined by the Autovacuum max workers variable in Postgres, setting in Postgres. Each worker can handle one database at a time, but multiple workers could process the same database. That means the default, by the way, is 3. So by default, at most, you have 3 processes working your vacuums for you behind the scenes as your server runs. You don't need to do anything. This just happens automatically when you start the Postgres server. Now, we've done a bunch of work in pganalyze to visualize this. If you want to try out pganalyze or are using it today, there's a vacuum activity view which tries to visualize this as a timeline and says, you know, these vacuum processes, what are they doing? What are they up to? So this can be helpful just to understand a little bit better visually how this works. Now, each worker process, right, each Autovacuum worker process, when it gets launched, which we don't talk about much right now, but let's just imagine there's reasons for it launching. Once it's launched for a particular database, it will check each table in that database and will execute vacuum and in some cases analyze as needed. Now, there is a problem here, as the Postgres documentation states, which is if several tables are all becoming eligible for vacuuming in a very short amount of time, then Autovacuum is going to be very busy. And this would result in other things not being vacuumed because these limited number of Autovacuum workers are going to be busy doing, you know, these large tables, and the other tables are just not going to get seen. It's kind of like an Autovacuum traffic jam, right? I luckily don't drive much, but if I would drive more, I would get frustrated, I'm sure, with Bay Area traffic. And really, you know, just imagine your Autovacuum workers to be the grumpy commuter kind of stuck in traffic often. Now, let's back up on a freeway. Let's not back up on a freeway. Let's back up for a moment. So why do things become eligible for Autovacuum in the first place, right? Why do we even vacuum a certain database or a certain table? Now, when we think about databases, which is kind of the first step in the process, Postgres looks at which of the databases was least recently Autovacuumed, right? So something was Autovacuumed just now that makes it less interesting. Or if we need to vacuum a particular database to prevent transaction ID wraparound related data loss, is how the documentation calls it here. So this means that Postgres in general will try to not vacuum the same database all the time. And the exception to this would be if transaction ID wraparound gives us a reason to keep looking at the same database. Now, if we find databases with transaction wraparound problems, then we look at the oldest one independently of when the last Autovacuum happened, right? So there's kind of this idea that we try to find the most urgent thing, the most urgent database to look at, and then we start working on a database. Now, quick tuning tip here, and we'll have a few of these throughout the rest of the presentation. But if you have hundreds or tens of databases, you should probably raise your Autovacuum max workers, because what can often happen is that your Autovacuum workers get busy and they'll care more about anti-wraparound vacuums than about regular kind of bloat prevention vacuums, which means that it's biasing towards a certain portion of your workload, a certain part of your database. And so it very likely is that your tables will bloat because there's just not enough Autovacuum capacity. And so that's why oftentimes if you have a lot of databases, it makes sense to raise that Autovacuum max worker setting. Now, let's talk about what we do for a particular table on a database. So generally, think of this as a for loop. It's literally, I guess it's a while loop, but it's literally looking at all the tables in the database. Like I looked at this code yesterday in Postgres, and it literally just gets a list of tables and just walks them, right? Like in a particular database. Now, the first thing it will do, and this is a simplification, but the first thing we'll do is we'll check are we hitting the freeze max age? So the freeze max age is a number in Postgres where Postgres says this transaction ID, the oldest frozen transaction ID, or none, I guess in a sense, the oldest frozen transaction ID, right? So the oldest alive transaction ID that's right next to it, is that kind of beyond our freeze age? So do we need to visit this table to advance the frozen X ID? If it is, start an anti-wraparound vacuum. If it's not, do the same check for MultiXact transaction IDs in the MultiXact freeze max age. If that happens, do an anti-wraparound vacuum. Now, only now, we're checking whether Autovacuum is turned off for this table. So you may not notice, but Autovacuum will run even if you turn it off, if it's for anti-wraparound reasons, because Postgres really does not want you to run into transaction wraparound. And so even if you turn Autovacuum off, either system-wide for some reason, don't know why you would do that, but either system-wide or on a table, Autovacuum will still trigger these anti-wraparound vacuums. Now, the regular vacuums, they will only go when Autovacuum is enabled. Then we'll check two things. We'll check if the modified tuples on the table are higher than the threshold. We'll get to the threshold in a moment. Or if the inserted tuples are higher than the insert threshold. And if either of those are true, then we will go and trigger a normal vacuum. Now, there are cases here where we do the normal vacuums or the anti-wraparound vacuums, or there are cases where we don't do any work. In any case, what happens next is we go to the next table, right? So Autovacuum runs for the whole database for each table, either doesn't vacuum or doesn't do a vacuum, and then it's done. It picks the next database. Might be the same database again if the transaction ID makes it so. A quick interruption here with multi-exact IDs. So this is a complicated concept, and we already have way too much content here. But if you have a problem with multi-exact transaction IDs, just know that there are limited finite integer space as well. They're used for concurrent row level locks by different transactions. So it's a function of your workload. If your workload does a lot of locking of the same rows in Postgres by different transactions, then multi-exact IDs are going to be a problem. Oftentimes you just don't need to worry about this. If you have this, you will see anti-wraparound vacuums for multi-exact reasons, not just for transaction ID reasons, because again, it's a similarly limited space. Also, if you have a lot of these multi-exact transactions or transaction IDs, then you will have a multi-exact anti-wraparound vacuum when your multi-exact members folder exceeds 2 GB in size. This is a very hidden attribute, but I was talking to somebody recently who they couldn't figure out why Vacuum wasn't doing its job. Vacuum was just not working on the tables that they thought it should be working on. And what they found out in the end is that it was because of multi-exact anti-wraparound vacuums. So this multi-exact anti-wraparound vacuum kept causing the wrong part of their workload to be vacuumed and the other part of the workload to be ignored. by vacuum. So it can matter in certain cases if you're seeing your vacuum behave erratically and you know you're using multi-exact IDs, then this type of stuff is important to know about. Now, back to regular transaction IDs, oftentimes it makes sense to raise the freeze max age. I'll show you a diagram of this in a moment, but the freeze max age says when to kick off a regular anti-wraparound vacuum for transaction IDs. And we usually want to reduce that on a lot of the databases that I've seen, because the default of 200 million transaction IDs for this limit is just very conservative. So 400 million or something is a good starting point to think about. The other thing I want to mention here is vacuum thresholds. So this is something that we've visualized in pganalyze, but it's just based on the data that you can get yourself easily. It's just easier to think about this visually. So we're looking at a particular table, and the red line we see here, this is what I would call the threshold, the vacuum threshold. So in this particular table, we have 120 million rows, and the Autovacuum threshold, the time when Autovacuum will trigger a normal vacuum, is going to be 11 million. And the math here is we multiply the number of live tuples by the Autovacuum scale factor. So you can see here in the middle on the right, the Autovacuum scale factor is 10%. So 10% of the table have to have changed. And also 50 tuples have to have changed, which is the Autovacuum threshold setting. So both of these combined give you the threshold. And when that threshold is met by the number of rows you've modified, then we'll see kind of a Autovacuum kickoff. Give me just a second here. Just realized logistical issue that I did not see earlier. So give me just a moment. I see. Yes. Okay. All right. Manny in our team wasn't able to send you messages, which was a Zoom configuration issue. Hopefully that's fixed now. Thank you, Manny, for pointing it out to me. So the two different vacuums that we have here is, so we have threshold-based auto vacuums. They will trigger when we hit the threshold, and then we have the anti-wraparound vacuums. They will hit at any time. They won't relate to this, right? But we can see this in this graph, how the dead rows relate to the threshold. Now, you can tune these Autovacuum thresholds on a per table basis. So you can go in and you can change table and you can set the Autovacuum scale factor, for example. Oftentimes, what I would recommend doing, this is another tuning tip here for you, is if you have a large table with a small active portion, you should turn off the percentage-based scale factor, because that will be very high, right? Like you saw earlier, this table of 120 million rows means 11 million have to change for vacuum to trigger. And so it often makes sense for these large tables to instead set the scale factor 0 and then set the threshold to a fixed number like 10,000, 50,000, 100,000, and then vacuum will kick off based on that. All right, let's talk about cost delay a little bit. So cost delay exists to slow down auto vacuum. And really the point is that we want to reduce our impact on other activity. So we don't want to have auto vacuum mess with our workload. So the way you can think about this is there's essentially 3 different types of activities. There's the vacuum cost page hit activity, which is when vacuum was trying to read something from a shared buffer cache, and then it got, it found the result in a buffer cache. The cost page read, which is when vacuum loads something from the disk or the OS page cache, and a page that was dirtied, which means the data was written out by vacuum. And so each of these accounts for a certain number of units, either 1 unit, 2 unit, 20 units by default. And then when you kind of do this activity, like the auto vacuum will account for these units. Now, when the auto vacuum cost limit is reached, which by default is 200 units, so for example, 10 times a page dirtied, then auto vacuum will sleep. And auto vacuum will sleep for the auto vacuum cost delay, which on modern Postgres versions is 2 milliseconds. So what that means is that auto vacuum throttles its own activity through this cost mechanism, right? So as these costs accumulate and you hit these limits, then auto vacuum stops the work for just a short moment and then it resumes to work again. And effectively what this does is it limits how much IO bandwidth throughput the vacuum uses, just because it doesn't, keep pushing the system to its maximum. Now, The server-wide Autovacuum cost limit is actually split between Autovacuum workers. So if you have a lot of workers, be aware that the cost limit may also need to be raised. But if you override it for a particular table, then it actually gets reserved fully for that particular worker. So if you do individual per table overrides, be conscious that that actually means that a worker gets its full cost limit times of work, right? So here, if I raise my cost limit, I do more work. Or if I lower my cost delay, I also work faster. And so if I override this for a particular table, then I get the full cost limit or delay. Now, if you are in a Postgres release that's older than Postgres 12, hopefully that's not many of you today, and you are modern hardware. Well, if you're running something old in Postgres 12, maybe you're not a modern hardware, but this has been the case for a while now. You should set your server-wide Autovacuum vacuum cost delay to 2 milliseconds, because this is what Postgres itself changed in the Postgres 12 release. And this was, community discussion, and the conclusion that was made is Autovacuum is just too slow. Like the cost delay settings were just too conservative, and it was just not running vacuum fast enough. And so definitely check this if you're an older Postgres release or you applied an old configuration to a newer version. Just make sure you don't use the old setting of 20 milliseconds, which is just very slow. And if you want to know more about how this looks like, you can look at pganalyze progress vacuum. This again, here's a visualization of that data. But pganalyze progress vacuum shows you how fast the vacuum is running, and also shows you how it's going through different phases. Now, I want to talk next about what parts of our table Autovacuum actually has to look at. So let's talk about what an aggressive vacuum and a failsafe vacuum are. Now, talk about aggressiveness first. So a normal Autovacuum, when it does its job, is it will visit all the pages in your table that are not yet marked as all visible. An aggressive Autovacuum will visit all pages that are not yet all frozen. This will include all visible, but not yet frozen. So usually the aggressive vacuum visits a much bigger portion of your table. One way to think about this is, you could actually run this, but I wouldn't necessarily recommend it. Autovacuum is fetching all the data from your table and is checking the visibility map to say either all visible or all frozen, depending on whether it's normal or aggressive. Now, is a particular vacuum aggressive? Like, how does it become aggressive? This is where it checks, again, this frozen XID, like the oldest transaction ID that's frozen in a table. And if that's beyond what's called the freeze table age, which is usually 150 million transaction IDs, then a vacuum becomes aggressive. It's important to note that this is not the same as an anti-wraparound vacuum. This confused me a couple of weeks ago, because an anti-wraparound vacuum is a scheduling decision, but an aggressive vacuum is really a vacuum is already running, and is it aggressive or not when it's running? So just by virtue of how the settings work, anti-wraparound vacuums are almost always aggressive. But threshold-based vacuums, right, what we talked about a moment ago, they can also become aggressive based on the transaction ID age. Now, both a normal and an aggressive vacuum will freeze pages, but the goal of an aggressive vacuum is to do this as its main thing, versus for the normal one, it's kind of, you could say, an eager decision for it to do it ahead of time. Now, which pages get frozen by vacuum, right? Like which part of our table is actually frozen? So if we freeze everything, then it actually causes a bunch of write IO, right? Because a freeze is ultimately a write on that page. And so we don't want to do that if we change the page soon again. Vacuum will actually be conscious of that. And so we'll only freeze transaction IDs and pages where the age of the transaction ID is older than the vacuum freeze min age, which is 50 million. Now, there's a bunch of numbers, so I'll try to show it to you visually. So coming back to our transaction ID clock, right? So we have 2 billion transaction IDs in total that we can work with. And out of these 2 billion, the first limit to think about is the vacuum freeze min age. This determines when freezing starts. So less than 50 million, like very recent write to the table, is not going to get frozen because the expectation is it's likely that we'll touch it again. Vacuum freeze table age is the time when a vacuum becomes aggressive. And so that's, soon after kind of the freeze min age, but not too soon, right? So the idea is that, there's some room for normal vacuums to occur. And then a freeze max age, that's the time when anti-wraparound vacuums kick off. And so what you can do is you can adjust these settings, right? Like you may actually want to push out the freeze max age and then maybe also push out the freeze table age, because really, they cause you to do more work. And oftentimes these defaults cause a busy database to do a lot of vacuum work that could be batched together better if it ran later. Now, there is something here that I want to highlight to you. So we have this freeze max age of 200 million, but there is actually, you can see this little X here, right? So the snowflakes, those are the frozen XIDs. There is actually one that got through. Now, why would that be the case, right? Didn't we exceed that freeze max age? Now, the reason that this can happen is because the freeze max age just says, for scheduling purposes, we should now really start a vacuum. So either if your Autovacuum worker capacity is just way out of whack, or you have a really long-running vacuum, what will happen is that, maybe the vacuum is running, it hasn't finished. I often see people in Postgres Slack being sad about a slow-running vacuum. And so, time passes, and then at some point we have to shut down the database and manually vacuum it, right? Because that vacuum still hasn't finished. And so that transaction ID hasn't become frozen, and that's a problem. One really important thing to understand here is that anti-wraparound vacuums do not run at full speed. They do actually take cost delay into account. This confused me some time ago, and I thought anti-wraparound vacuums do run at full speed, which would make things very differently, but they do not. They do slow down. So if you have a very slow anti-wraparound vacuum, it's very likely that the cost delay is to blame. Now, vacuum runtimes also heavily impacted by index sizes and amount of indexes, because vacuum does a lot of index cleanup work, which we won't talk much about today, just in the interest of time. But vacuum runtime can be very long for a table with a lot of indexes. And so what Postgres 14 introduced is a pretty amazing concept called a failsafe vacuum. And this should hopefully prevent a lot of people from ever seeing transaction wraparound warnings or issues on a database, which is a failsafe vacuum will trigger 1.6 billion transaction IDs by default. So it's very late in the cycle. But what it will do is it will skip all index vacuums and it will ignore cost delay. So we're on full speed. And really the point here is we just want to get those table pages frozen, right? Like we know we're in a pinch, like we're running out of time. And so we're trying to get things frozen so that we don't crash. This, I think, is a very, very good change that Peter Gagan made in Postgres, which I think will really save a lot of people, and they won't even know about it. They'll just do its work. Now, we probably want to do things ahead of time, right? We don't want to trust that failsafe, rely on a failsafe, or maybe an older Postgres. And so, if you have very large tables with a lot of activity, where vacuum takes long, do think about either increasing cost limit or reducing cost delay, because otherwise, they don't finish on time and we run into all these problems. You could also consider lowering your Autovacuum freeze min age. This is something you would want to do on a per table basis. But what that would do is if a normal vacuum happens and it's already looking at a page, then it could do more eager freezing. And this would then delay a future anti-wraparound vacuum and keep more vacuum capacity for the rest of the system. There is a proposed patch by Peter Gagan that tries to do a little bit like that in a more sophisticated way. But in older Postgres versions, I think it's worth experimenting with this. But be careful that you don't cause a lot of I/O by doing too much of this, essentially. So large tables only. All right. We're getting close to the end here. Looks like 45 minutes is not going to cut it. I'll probably go a little bit over on that time. So we'll probably have another 10 minutes of content or so. So I want to talk a few edge cases here because I think they're important, and then we'll get to the Q&A. So that tuples not yet removable. So if you are running a database, I would highly recommend you turn on log Autovacuum min duration. Now, what log Autovacuum min duration does is it's a threshold setting, usually I just set to 0. That means every Autovacuum that runs will log to the Postgres logs its activity, like how long did it run, what portion of the table did it look at, and such and such. This is amazing diagnostic information that does not exist anywhere else in the system, so just turn on that Autovacuum logging. Now, here's a particular case of where this is helpful and you had a problem with your Autovacuum. So if you see the tuples line roughly in the middle there, and that's output, you see that there were 0 tuples removed. There were 150,000 that remained in a table that are alive. And there's 26,000 that are dead, but not yet removable. So we know that there is data that we could remove, but we cannot because of visibility rules in Postgres. And we just spent 2 minutes looking at this table, looking at all these 26,000 rows, right? And we did nothing useful because we didn't actually remove anything. We didn't actually mark anything useful. And this is a problem because we'll run again and we'll run the same thing again and we'll not do any work. And so if this happens, and this happens a lot, you'll waste a lot of vacuum capacity and a lot of I/O. And the reason that these dead tuples not yet removable occur, most of the time is long-running transactions. So if you have a long-running transaction, that can really mess with vacuum. And I'm saying long as in hours or days, right? Like if it's like for a couple of minutes, that's fine, I guess. But if you have a transaction that's open for multiple days, that will really cause you issues on your vacuum performance. And so you can check that if you look at the backend xmin and backend xid and pganalyze activity. But that's something to verify if your vacuums are just running into the dead tuples, not a removable problem. There's some other edge cases like forgotten replication slots. Hot standby feedback can mess with this, or prepared transactions if you're using them. But really, long-running transactions is the main thing I would check if I see these dead tuples not yet removable. Now, let's briefly talk about vacuuming in the cloud. And let's talk about, well, the most common providers I see. So Amazon RDS and Aurora have something that's called adaptive Autovacuum. Now, adaptive Autovacuum, it's actually pretty simple. It's not necessarily as adaptive as the name might make it seem. So it triggers when the transaction ID reaches, my understanding, 500 billion transaction IDs. I believe it was 750 million transaction IDs at some point in the past, but they changed it to 500 billion. And so what happens is at that point, the adaptive Autovacuum special logic in RDS or Aurora triggers. And what it does is it reduces the cost delay and increases the resource consumption. So what it actually does is it literally just changes parameters. So when you have, this number of transaction IDs, it messes with the cost delay, the cost limit, the workman, and the nap time. And it does that in order to make vacuum more aggressive. This is essentially a poor man's version of a failsafe vacuum that tries to trigger early and tries to do more work early. Now, I would recommend to not rely on that at all. This is just something that they added because they probably had their support teams, being contacted all the time because people ran into, transaction wraparound problems. But really, you should tune per table vacuum settings instead and have regular vacuums do the work ahead of time. Now, Aurora has something else that's really, really interesting and confused me when I saw it. So Aurora also has Autovacuum. Oftentimes people ask, does Aurora do this? Does Aurora have that? Aurora does not have checkpoints. That's a different concept, but it's good to know. But Aurora does have Autovacuum. Now, Aurora does something with the costing with Autovacuum to model their, fork of Postgres. So Aurora defaults to vacuum cost page miss of 0 and a cost delay of 5 milliseconds. So the page miss to 0 is very interesting because usually the idea behind the vacuum costing is if something is not in cache, it's more expensive. And so we need to penalize ourselves for it and slow ourselves down. And the idea is that, that just reduces the I/O contention. What they've done, though, is they've said page miss is 0, presumably because they have a page server. And so they're actually not as much worried about the higher concurrency on the Aurora storage subsystem because you have that page server. And they probably want to have, I/O requests merged together. And so it's actually better to do more work at the same time. Now, what that means, of course, is that your Autovacuum cost and your Autovacuum kind of performance will behave differently than in other systems. And so just if you're looking at, what vacuum is doing, just be aware of this aspect of the system. Now, Cloud SQL and AlloyDB, I wish Google generally is good with documentation, but I couldn't find good documentation on what they're doing here, sadly. So if anybody from Google listens to this at some point, please improve your documentation. So Cloud SQL, this is from a pgconf.eu interview a couple of weeks back. So Cloud SQL has what's called emergency maintenance mode. And my understanding is it's essentially a way to do what's called single user mode without being in single user mode. Like it gets you some extra transaction IDs to go into the database and run a manual vacuum. And it's something you have to enable for a parameter, in my understanding. It's probably something the support will tell you when you reach out to them. But the point is it helps you when you're in a pinch, like when you really are close to the things shutting down. This helps you do something like single user mode vacuum. Now, AlloyDB actually is a lot more complicated here. Sadly, also not documented yet from what I found. But they make modifications to Autovacuum where they're reallocating more resources to Autovacuum by saying, well, Autovacuum is clearly not doing enough work. We need to give it more resources. What they also do, and I think this is really the net new thing that I've seen here, is they're throttling how many incoming transactions you can make when you run out of transaction IDs, right? So again, remember, all of this is a function of your workload. If you're assigning a lot of transaction IDs, if you're making a lot of transactions, you will run out of transaction ID faster. And so what they've added in AlloyDB is they're slowing you down at some point because they want to prevent the imminent shutdown, and they're doing that by slowing down your workload explicitly. So I think that's probably a good idea. But again, I wish there was more documentation here. Now, the very last quick topic here, which is estimating and fixing table bloat. So I just want to get back to this, and this is intentionally at the end. So let's go back to this. In the beginning, we had estimating, like we had a bloat situation, right? So we had these 2 pages, and we had a very low page density. Now, this was actually something that we saw in our own database, which is why I ran something last weekend. Because if you look at this pgstat tuple output here, you can see that there's 95% of the table is free. Now, this is a 500 gigabyte roughly table, and so only 1.7% of that table is actual data. Everything else is free space, right? And this was an application bug. We did a lot of updates. There were not hot updates, and we essentially messed with our table. Really, if this was a problem on the application side. However, it costs us this table bloat. And I like to think of table bloat as a less than optimal page density, like how many tuples are on the page versus how many could actually fit there. Now, you may be familiar with bloat estimation queries. Here's a popular one. Well, here's 1/5 of a popular one. They're pretty scary and complicated. I tried understanding the math of them again the other day, and I think I understood the math, but it's a bit sketchy. Like, it's kind of weird how they're run by everybody, and people don't really understand what's happening, and they're just copying them around and maybe using one version or the other version. So I'm kind of on the fence whether they're a good idea or not. The idea behind the bloat estimation queries is simple. So they look at how many tuples you have in your table, which the last analyzer vacuum will have told you. They'll look at the average column width of data in your table as collected by Analyze. They'll look at the alignment of columns as defined by your platform. And if you have fill factor, some of the estimation queries also look at fill factor. Now, based on that, it will calculate what is the optimal size of the table if everything was packed the best way, right? Like if we try to fit as much tuples in a page as possible. And how does our current table size compare to that? And so when a bloat estimation query gives you a number that says bloat, really what it means is the difference between the optimal size of the table and the current table size. Generally, I would say look at pgstat tuple functions that we showed you earlier much more than these bloat estimation queries, because pgstat tuple is maintained by the Postgres core team, and it gives you a lot of similar data. So I'd much rather run pgstat tuple on a database or a table. If you do use bloat estimation queries, use Analyze. That gives you an accurate rel tuple count, somewhat accurate rel tuple count, and that's important for bloat estimation. And if you have very large columns, then your average column width may not be correct, right? Because Analyze is going to sample a subset of your database, your table, and so the number might just be completely off. And if you do the index bloat estimation queries, just be very careful. Their math is even more, I think, suspicious. And so I would be careful there, and I would probably do a reindex on a copy of the database instead of really relying on the index bloat estimation. But if we do vacuum on a bloated table, it doesn't actually fix the bloat. And this is really the last point I want to make here, which is vacuum does not move around rows, right? Vacuum just goes in and marks that rows as reusable or pages as all visible or all frozen. And so it helps our workload use the space efficiently, but it does not rewrite the table unless you're doing a vacuum full. However, people don't use vacuum full on production databases. And so that's where pgrepack comes in. So vacuum full or pgrepack will do a rewrite of your table to be as efficient as possible. And it does that in the case of vacuum full with an XX exclusive lock. That's not realistic, but we don't want that. pgrepack does most of its work online. And so the way we run this is we create an extension pgrepack. This is a community extension that's not in the core Postgres. So you might have to install it. And then you both need the extension and the client utility. And the way you run it is you specify your host name, you specify a table name, connection details, and then you run it. You have a dry run option as well. And whilst it's running, what it's doing is it's creating a copy of your table. It's also creating a trigger to track changes, and then it writes all these changes into the kind of new table at the end, and then it kind of switches around the files. And so it's mostly an on-on operation. There's a very short exclusive lock at the end. It's kind of like a reindex concurrently from a locking behavior perspective. And this is how we fixed our problem, right? So we ran pgrepack because Vacuum did not do its job, because we messed up our workload and we didn't tune the Vacuum settings. And we ran a repack and it was fixed. But if we have bad workload again and we don't change Vacuum settings, right, what will happen is we'll just end up in the same place. And this is actually something that we referenced in our previous webinar on I/O performance, but I think it's just good enough to mention it again, is if you do repack, it will actually save you money, because bloated tables are inefficient, cause you more I/O, and that's expensive, especially with things like Aurora. And so repack really has a direct impact on the bottom line. But again, you really want to do the Vacuum ahead of time. There's 3 things we didn't talk about today. As you can see, we're already over time on the content portion of this, but we didn't talk about hot updates and opportunistic pruning. So read up on that, because oftentimes that helps you avoid a table-wide vacuum or save kind of a lot of work, because updates and pruning kind of cleanup work is done ahead of time. We didn't talk much about index vacuuming or index bloat. I think that could fill its own webinar, but that's a longer topic. And we didn't talk about Autovacuum work mem tuning. So work mem will kind of related to index vacuuming mostly, but that's something that you may want to look into if you have very complex tables, like large tables with lots of indexes. Look into the work mem setting as well. And yeah, that's really it. Thank you so much for joining us today. I'll get another sip of coffee, and then we'll look at a Q&A. And if you have any more questions, please feel free to post them in a Q&A. Looks like we have a good number of questions. If there are any questions that we don't get to today, what we'll do is we'll send it out by email. So we'll answer the questions kind of async, and then we'll send out an email. But I'll try to capture a few of them now whilst we're here. Let me see. Yeah, so that's actually a good point. Somebody brought up that this does not exist in MySQL. It's Postgres specific. Is this Postgres specific? And yes, of course it is, right? Like this is, if you, all of this is very Postgres specific, and there's reasons for why it is this way. But yeah, MySQL works differently. I forget how AlloyDB handles these things exactly. But the point is, this is Postgres specific. And really, if you're coming from Oracle or MySQL or other database systems, I really read up on this stuff, try to understand it, because it impacts your database so directly. Let's see. There was a question on, does transaction ID wraparound only happen when the age of transaction IDs goes past 2 billion? So if the maximum value is passed, will you immediately have corruption? Yes, is what I would say. So if you try to advance the horizon beyond those 2 billion, you would have this effect that I showed earlier, which is you would have a row that suddenly appears to be in the future instead of the past, and so you will get data corruption in the sense that your database returns you wrong data. That's what you would get at the 2 billion mark. Let's see. Okay, so there was a clarification question with that. And did you say that only one Autovacuum worker can be active for a given database at a given time? So no concurrency within a database, but concurrent vacuums on different databases are permitted. Yeah, so let me clarify this. So each Autovacuum worker process runs on one database at a time. However, there can be multiple Autovacuum worker processes working on the same database. And what happens is there is a kind of coordination mechanism, and Autovacuum worker will skip a table that the other one just worked on and such. So there is kind of coordination. So it could happen if you just have a single database on your server, that your 3 Autovacuum workers will actually work the same database, but they'll all start working the tables from the beginning and down. So the scheduling isn't very smart in that case, I would argue. Let's see. I'll probably do like 2-3 more questions. Let's see. There was a question from Dave. What are some caveats when raising Autovacuum Max workers? I think that's a good question. So Autovacuum Max workers, if you raise it, as mentioned, it's related to the cost limit. So it tries to be smart about a higher number of workers and not necessarily cause you more IO right away. Now, assume you also raise the cost limit, right? You're essentially trading off Autovacuum capacity, like increased Autovacuum capacity for, in the worst case, a higher peak IO impact. And you also have a higher CPU usage by Autovacuum because there's just going to be more of them running, right? It's just going to be more cycles. But that said, if you have a backlog of Autovacuum, then you probably really want to raise the max workers and potentially adjust the cost settings. Oh, this is a good question. So is there a situation when it's better to not use Autovacuum and stop vacuuming at all? If you don't assign any transaction IDs and you don't make any changes to your database, then maybe you don't need Autovacuum. However, the problem is there are a couple of internal processes that will assign transaction IDs. And so even in that case, you will eventually need an anti-wraparound vacuum. And so what some people do in terms of manually running vacuum is they run vacuum once a day at night, for example. And you can do that. That's actually not a bad idea. But what I would consider doing is leaving Autovacuum turned on, because it shouldn't trigger if there's no work to do, or turning it off on a per table basis. So if you are really sure that your Autovacuum isn't needed on a particular table, then you could consider turning it off on that table that you're manually vacuuming. And Postgres will actually ignore you if needed and do an anti-wraparound vacuum. But yeah, like it's something I'd be really careful with. Generally, Autovacuum is a good thing to just leave turned on and do extra vacuums if needed. All right. There was an important question by John on pgrepack and whether pgrepack is safe, and because they heard about data corruption after running it on big tables. So my understanding is that pgrepack these days is fairly safe. That said, it is not in core. And so pgrepack is a community tool that, you have to be aware that there might be bugs. I felt safe running it the other day. But pgrepack is something I wish would be core, hopefully one day, so we have kind of more guarantees around its stability. And I think in the interest of time, I think we'll close here, but we'll get to the other questions. There were a lot of other questions, but I want to get to them by email, and I'll send them to you by email tomorrow with the answers. In the post-webinar survey, you'll get 2 questions, by the way. When you're interested in a demo of pganalyze, let us know. And then also we're starting to add some new features to pganalyze around Autovacuum tuning. So if you want to give us some feedback on these new features in the post-webinar survey, you can also tell us about that. And then we might schedule some time with you to hear more about your workload, your use case, and how we can help. So thank you so much for joining today. Really appreciate your time, and have a good rest of your week.